Hello viewers, welcome back to this channel. So in this video you're going to be proceeding with transition chemistry and you're going to be looking at the chemistry of cobalt together with nickel. So this video is presented to you by Olgembe Yusuf and you're advised to subscribe to the channel and share the video to your friends so that you can all benefit as a group. Now proceeding from where we have stopped, remember that in the previous video we looked at the chemistry of iron together with its qualitative analysis and we looked at all the examinable areas. So this is the second last video, and in this video we are going to be looking at cobalt or the chemistry of cobalt together with the chemistry of nickel as required by the NCDC syllabus. Now the last video is going to be handling copper together with zinc as the concluding elements under transition metals or elements. Now starting with cobalt, let's first look at the reactions that are going to be undergone by cobalt. So we're going to look at the reactions with air. Now since I've overemphasized reaction conditions, I'm not going to be overemphasizing them also in this video. This video is supposed to be brief because the chemistry of cobalt and nickel does not require depth of understanding, but we just require to know specific reactions because also cobalt is not examinable and the practicals that are carried out at advanced level. So you'll be looking at it in details when you proceed to the university. So looking at the reactions of cobalt, you're going to start with the reactions with air. Just like we said that any statement before writing an equation must contain the conditions together with the products that are being formed. So heated cobalt always reacts with air. So there's a missing word there. Heated cobalt reacts with air to form tricobalt tetraoxide. And the balancing is going to be the same as that one of iron, because also when we heat iron in oxygen we get tri-iron tetraoxide, and the same applies to cobalt. So when you heat cobalt in air, you are going to get tricobalt tetraoxide, and that is done in presence of sufficient oxygen. Now the other reaction is going to be the reaction with water, and we are going to say that cobalt does not react with cold water, so we must have specific conditions for cobalt to undergo a specific reaction. So that's why we're going to say that heated cobalt, so the condition here is that cobalt must be heated, and we say that anywhere where there is heating and water is involved, that means that water is going to exist as steam. So the condition is water is to be existing as steam, so as cobalt to react with water. So heated cobalt reacts with steam to form tricobalt tetraoxide and hydrogen gas. Now notice that these reactions are similar to the reactions that we looked at under the chemistry of iron. So three cobalt molecules react with water molecules to form tricobalt tetraoxide together with hydrogen gas. Now I'm not going through how we balance equations because I believe I've overemphasized that concept. Now let's go to the reactions with acids. Now first of all, you're going to start with dilute acids. Now we're going to say that cobalt reacts slowly with hot dilute hydrochloric acid together with sulfuric acid, liberating hydrogen gas, and also it forms slowly the corresponding cobalt 2 salts present in solution. And the general equation that you're going to have for that is going to be the cobalt existing in the solid state reacting with the hydrogen ions or the protons to represent an acid, either dilute hydrochloric acid or dilute sulfuric acid, so as to form the cobalt 2 salts together with hydrogen gas. Remember that whenever you react an element with an acid, you are going to form a salt together with hydrogen gas. But whenever you react an oxide of an element with the acid, you are going to form a salt together with water. So you have to be serious at knowing that. So if you go to the other reaction, you're going to look at the reactions with concentrated acids. Now you're going to say that cobalt is oxidized by, now remember I told you, hydrochloric acid, however concentrated or dilute, it is not an oxidizing agent, or it's not an oxidizing acid. The only oxidizing acids that we have is concentrated sulfuric acid together with concentrated nitric acid. But I told you that the background behind concentrated nitric acid is that most of the transition elements render it passive. That means that most of the transition elements do not react with concentrated nitric acid. So cobalt is going to be oxidized by hot concentrated sulfuric acid to form cobalt to sulfate, and then the acid, after oxidizing, it gets reduced to sulfur dioxide together with water, and the equation is going to be this one. And this equation is a redox equation, and I hope, like I'm overemphasizing using redox reactions to get to now to balance these equations, because it's the easier way you can move out the paper confidently, knowing that you have written all your equations correctly, apart from representing the states. So whenever they are marking your equations, we shall look at three things. An equation is given 1.5 marks. So if you miss any state of a compound or an element in your equation, either in the products or reactants, you are going to lose half a mark. But if your equation is unbalanced, you do not gain any mark. So if you miss any state, you gain 1 mark. If your equation is unbalanced, you don't gain any mark. So it is left unbalanced. That's why understanding equation balancing is very crucial before you go deeper into the chemistry of transition metals. So cobalt is rendered passive just to concentrated nitric acid, just like any other transition element. So going to the reaction part D, we are going to look at the reaction with chlorine, and we are going to say that heated cobalt is going to react with dry chlorine gas to form cobalt to chloride. If you look at this statement is containing conditions, and the conditions here are heated cobalt reacting with dry chlorine gas to form cobalt to chloride. And the equation is going to be as follows. Balancing follows the same criteria, just like we looked at it in the previous videos. And if you have any concern about any of the explanations given and you're still lacking somewhere, you present your concern in the comment section. Now, many of you come to my WhatsApp and try to contact me, but I leave you largely unanswered, because always my WhatsApp is clogged with a lot of inquiries from students. But it's better you quote your concern on a specific video so that I can get where to start in explaining where you are lost. Now let's go to the reactions with alkalis. So we're going to say that cobalt has no reaction with any alkali. The reason for that is because cobalt is mainly basic, and there is no way basic component can react with a basic compound. So alkalis are basic, also cobalt is basic. So unless cobalt is in solution is when it will react with alkalis. But if it's not in solution, cobalt as an element does not react with dilute or concentrated alkalis, and that is sodium hydroxide or potassium hydroxide. So proceeding, you're going to be looking at the compounds that can be formed by cobalt. So you're going to say that cobalt has two principal oxidation states, and one of them is going to be the +2 together with the +3 oxidation state. And here is the +2 oxidation state, which is going to be the most stable, and you can find out the reason why by writing the configurations for both the +2 and the +3, and then start comparing the configurations with the explanations that we gave in the previous videos, and I think you'll be seeing the elaborative answer for that by your own eyes. So you're going to say that the +3 oxidation state is mainly found in complexes. So let's look at some of the compounds that are going to be formed by cobalt in the +2 oxidation state. So first you are going to start with the cobalt oxide, and you're going to say that cobalt oxide is a green solid that can be obtained either by heating cobalt hydroxide or cobalt carbonate or cobalt nitrate. Remember that whenever you heat a carbonate, you get an oxide together with carbon dioxide. So when you heat cobalt carbonate, you are going to get cobalt oxide together with carbon dioxide. And when you heat a nitrate, remember that whenever you heat a nitrate, you get nitrogen dioxide gas together with oxygen, except the nitrates of group 1 elements or metals. So heating cobalt nitrate is going to give us cobalt oxide, which is the main compound we need, together with nitrogen dioxide gas together with oxygen. And the balancing follows the same criteria like we mentioned before. So when you look at cobalt oxide is going to be a basic oxide that reacts with dilute acids, forming pink solutions of cobalt salts, or forming solutions of pink containing cobalt salts, or containing cobalt ions within them, such as test solutions. So cobalt oxide reacts with an acid or any other acid or any dilute acid to give us cobalt ions, which make the resultant solution or the test solution to appear pink, and also water is formed as another product. Now furthermore, looking at the chemistry of cobalt hydroxide, we are going to say that since cobalt hydroxide is also in the plus oxidation state, the problem with complex transition elements is that they have compounds existing in varying states. And the reason for that is because of paramagnetism, which we explained under the introduction introduction video of transition elements. So what you're going to say is that cobalt hydroxide is going to be a blue precipitate, which is obtained when aqueous sodium hydroxide is being added to a solution containing cobalt ions. So when you're having a solution containing cobalt ions and then you add sodium hydroxide, the hydroxide ions from sodium hydroxide react with a cobalt ion to give us a blue precipitate of cobalt hydroxide. Now we are going to also cobalt hydroxide, just like cobalt oxide, both are basic and therefore both react with dilute acids to give us cobalt salts in solution. So cobalt hydroxide reacts with a dilute acid to give us cobalt ions and then plus water as another product. Now let's look at how we can obtain cobalt chloride. Now since cobalt has its most stable oxidation state to B+2, both chlorine as an oxidizing gas and also hydrogen chloride give the same products. So chlorine is an oxidizing gas, but it won't push it to the +3 oxidation state because the +3 oxidation state is more unstable as compared to the +2 oxidation state. So whenever you heat chlorine together with hydrogen gas, we always get a chloride which is in the +2 oxidation state of cobalt. So you're going to say that cobalt chloride is going to be an anhydrous salt which is blue in nature and is obtained by heating cobalt in either dry chlorine gas or dry hydrogen chloride gas. So the equations are going to be as follows. Balancing follows the same criteria. You start with metals, you go to non-metals other than oxygen and hydrogen, you balance oxygen if present, and lastly we balance hydrogen in any equation. I say that equation balancing for any chemistry student at this channel is a must. So you should be very careful about that. You shouldn't pass through transition elements without mastering equation balancing. Now proceeding, we are going to say that if you look at the hydrated salt of cobalt, so the hydrated salt of cobalt chloride is going to appear red or pink in nature, but in most of the cases, since the existing solution is going to exist as pink. So for cobalt, is the only element that is either exists in pink or blue, other than copper. So you're going to say that cobalt chloride is going to turn pink in water due to formation of a hydrated salt, which is going to be called hexaqua cobalt ion. Now remember that in the introductory video of transition elements, I told you how to name these complex ions, and you should be very comfortable in writing them. Remember that I told you there's no space that is being left whenever you're writing a name of a complex ion, and that's where you lose your marks from. So the hydrated, remember that anything to be hydrated, that means that the ion or the cation has a high charge density, small ionic radius together with high charge density together with a high ionic charge, and that's what causes them to become hydrated whenever they are placed in solutions which contain water molecules. So all transition elements, their cations, since they have a small ionic radius together with high charge density, they exist as hydrated ions in solution, or complex ions, or the transition ions. So looking at another reaction, I'm going to say that when concentrated hydrochloric acid is added to such a solution, which is containing this sort of cobalt-2, this hydrated salt, or a saturated solution of potassium chloride is added to such a solution, the solution is going to change from pink to blue. And the reason for that is what happens is that we call it a ligand exchange. Now remember that ligands, we talked about that under introduction of transition elements. Ligands are those ones that are connected to the central metal atom. So what happens is going to be a ligand exchange, is that the chloride ions from potassium chloride are going to come up, or the chloride ions from hydrochloric acid are going to come and then they replace the water molecules. and then they replace the water molecules so that we form a complex of cobalt, which is called tetracobaltate 2 ion in solution, which makes the solution to turn from pink to blue. So note that whenever cobalt is hydrated in solution, that solution is going to appear pink, and whenever it's not hydrated, or it's a complex of another form other than water, it's going to appear blue, and that's mainly chloride. So the chloride ions from either hydrochloric acid or potassium chloride, they replace the water molecules, giving us a complex together with water. And we're going to say that this is called ligand exchange, whereby we move away, one ligand is replaced by another ligand. So that's a method which is called ligand exchange. So these chloride ions have replaced the water molecules as ligands in the complex, resulting into the color change. Now diluting the solution, if we dilute the solution more, if we dilute this solution which is contained in this complex, if you add more water molecules, remember that this is an equilibrium mixture. I taught you chemical equilibrium on this channel. So if you add more water molecules, this reaction reverses. And therefore, that means that the blue solution is going to turn back to pink, because the chloride ions are also going to be replaced by the highly concentrated water molecules that are present in the vessel. So that's why we are saying that here, diluting the solution results into reforming the pink solution. It's because this is an equilibrium reaction. Now let's go to the compounds that are present in the plus 3 oxidation state. Now we say that majority of the compounds that are present in the plus 3 oxidation state are going to be complex ions. So we're going to say that cobalt 3 does not occur in simple compounds, but it is stable. It's stable in formation of many complexes. So proceeding, let's look at the qualitative analysis of the cobalt 2 ions that are present in solution. Just like I've said, the cobalt in the plus 3 oxidation state is going to exist in complexes. And for such, the questions that can appear under there is going to be naming of complexes, which already looked at under Introduction of Transition Chemistry, which was video number 1. So looking at the qualitative analysis, let's look at the qualitative analysis involving sodium hydroxide solution. Now remember that I told you that most of the cobalt solutions containing the cobalt 2 ions are either going to be pink as a result of hydration, or they are going to be blue when cobalt is saturated. So when hydrated is pink, when saturated it's going to be blue. So observation, when you add sodium hydroxide, you are going to first observe a blue precipitate which is going to be insoluble in excess, but on standing it's going to turn pink. And let's look at the reason behind that. This is going to be due to the oxidation of cobalt hydroxide to hydrated cobalt 3 oxide by atmospheric oxygen by a method called area oxidation. So first of all is the reaction between sodium hydroxide and the cobalt 2 ions, forming the cobalt 2 hydroxide. Now this cobalt 2 hydroxide undergoes area oxidation by absorbing atmospheric oxygen. And when it does so, it's going to form cobalt 3 oxide, which is going to be hydrated. And he said that whenever any compound of cobalt is hydrated, it turns pink. So that's why your initial observation is going to be blue precipitate, insoluble in excess but turns brown on standing as a result of area oxidation together with being hydrated. Now going to another reagent, we are going to look at ammonia solution. Now with ammonia solution, the observation is quite different. So in ammonia solution, what you observe is, first of all, you're going to form a blue precipitate, and this blue precipitate is going to be due to formation of the hydroxide. But this precipitate is going to be soluble in excess ammonia, forming a yellow solution, which turns red on standing. And this is due to oxidation of our hexammine cobalt 2 complex. Remember that the hexammine cobalt 2 complex is what causes this yellow solution to form. Now what causes it to turn to red or brown is the oxidation of this hexammine cobalt 2 complex to turn to hexammine cobalt 3 complex in solution. And let's look at the equations. So in the first equation is a reaction between the hydroxide ions coming from ammonia solution to give us a blue precipitate of cobalt 2 hydroxide. So if you're writing your notes, you can put in brackets here that this is a blue precipitate. Now the hexammine cobalt 2 ion is what forms the yellow solution. So when the blue precipitate formed dissolves in excess ammonia, it gives us a complex of hexammine cobalt 2 ion and then the hydroxide ions in solution. But when we leave, now this is what we call the yellow solution. Yellow solution is due to formation of this compound or this complex which is present in the +2 oxidation state. But when this solution is left to stand, it is slowly going to turn into red, or other scientists call it brown, but it's going to turn into a red solution. And when that happens due to reoxidation. Reoxidation is when we absorb oxygen and water from the atmosphere to increase the oxidation state of any compound, either complex or a non-complex. So this complex stands from +2 to +3, and then +4 excess hydroxide ions. Now here, for some scientists, they just ignore the part of oxidation, and then they just take it to this compound with an increase in the oxidation state, and then they just say plus electrons. Also, that equation is valid. There are two equations, but this one is the most scientific because it shows atmospheric oxidation. But also the other one is also marked. So you can leave out oxygen and water, and then you just come from here. You just come from here, and then you draw an arrow giving you this compound. And then you don't write the hydroxide, you just say plus an electron to balance up the charges. Also, that one will be marked correctly. But it's less scientific because I presented this one because it shows or it celebrates reoxidation of the complex to another oxidation state. Now let's look at another reagent, which is going to be potassium thiocyanate. Now whenever you're adding potassium thiocyanate to a solution containing cobalt ions, we add drops of concentrated hydrochloric acid first for this reagent to act properly. So the observation that you're going to see is the blue solution, and it says that whenever you're forming a blue solution, that means that you're having a cobalt complex which is non-hydrated. So that complex is going to be called tetrathiocyanate cobaltate 2 complex. And I told you how to name complexes. So you make sure that you are very good in that field. So equation is going to be cobalt ions reacting with the thiocyanate ion to give us the tetrathiocyanate cobalt 2 complex without leaving any space in it, which is going to be aqueous in nature. And this is what gives us a blue solution. It's blue because it's non-hydrated. Now we are saying that if pentano or ether is added to the resultant solution or to this solution containing this complex, the blue color forms in the organic layer. So when you add ether, remember that ether is immiscible with majority of the reagents. So when we add it to the resultant solution containing this complex, is that you are going to observe a blue color present in the organic layer. And you can go and look through your practical books to see whether such a reaction was explained in details. So looking at this, number 4, we are going to be looking at the potassium nitrate solution. But whenever you're using potassium nitrate solution to a solution containing cobalt ions, is that we first add ethanoic acid first. So the observation is going to be a yellow crystalline precipitate of potassium hexanitrito cobaltate 3 complex. But here, whenever you're stating the observation, we do not need the name. I just give you the name here to guide you in naming these complexes for those of you who still have weaknesses. So the observation is a yellow crystalline precipitate or potassium hexanitrito cobaltate 3 complex. And let's look at the equation for that. So looking at the equation is going to be as follows. But such equations, they are going to be hard to be examined because rarely do we examine such equations. So I won't even try to explain it. So let's go to number 5, saying that potassium reaction or reagents with potassium cyanide solution. Now this one is highly examinable. So the observation is a reddish-brown precipitate soluble in excess forming a reddish-brown solution. So first of all, we form a reddish-brown precipitate which is soluble to form the same color of a reddish-brown solution. But this reddish-brown is containing a complex which is called hexacyano cobaltate 2 ion. So first reaction is going to be reaction between the cobalt ion and then the cyanide ion to give us cobalt 2 cyanide, which is a reddish-brown precipitate. By this reddish-brown precipitate in excess, it reacts to form a complex of the cyanide, which is called hexacyano cobaltate 2 ion. which exist as, for a complex, they exist in solution, and it makes our resultant solution from a precipitate to a reddish, from a reddish brown precipitate to a reddish brown solution. And that's what happens when you react cobalt, a solution containing cobalt, with potassium cyanide solution. I said that this is a very highly examinable question, and it can act as also a confirmatory reagent of cobalt, though at practicals we do not examine cobalt. Now looking at another chemistry, we're going to look at the chemistry of nickel. Now nickel is brief and clear, so let's start with the reactions. So under the reactions, we look at the reaction with air. Just like any other elements, we say that the statement must contain the conditions together with the product being formed. You can ignore the color. I just guided you with the color to let you know when you're handling it in practicals. So heated nickel reacts with air to form nickel 2 oxide, and the equation is as follows. So the most stable oxidation state of nickel is +2. So with water, it also reacts with steam. It reacts when heated, and whenever we heat, water has to be in terms of steam. So heated steam reacts with steam. Heated nickel reacts with steam to form nickel 2 oxide together with hydrogen gas, and the equation is as follows. Now looking at the reaction with the acid, we are going to say that nickel reacts with hot dilute acids to form the corresponding nickel 2 salts together with the hydrogen gas. So nickel as a metal reacts with aqueous acids to give us the nickel 2 salts together with hydrogen gas as follows, just like we mentioned earlier on. Now, just like any other transition element, we say that nickel is going to also be rendered passive to concentrated nitric acid. So it does not react with concentrated nitric acid at any condition. That's what we mean by rendered passive by concentrated nitric acid. And now looking at another reaction, you're going to look at the reaction with chlorine. So heated nickel reacts with dry chlorine gas to form nickel 2 chlorine. Just like I said, nickel has the most stable oxidation state to be +2. So nickel reacts with chlorine to give us nickel 2 chloride, and the same applies to hydrogen chloride gas. That I didn't include the reaction, so you may fix it somewhere. So compounds that are going to be formed by nickel. Now nickel usually forms compounds in the +2 oxidation state, and then nickel 2 compounds are going to be generally green throughout all its chemistry. Now let's look at the chemistry behind nickel 2 oxide. So nickel 2 oxide, just like any other oxide or cobalt, the oxides of cobalt, it can also be obtained by either heating nickel 2 carbonate, nitrate, or an hydroxide. So whenever you heat an hydroxide, you're going to get an oxide of nickel in the +2 oxidation state together with water. Whenever you heat nickel 2 carbonate, you're going to get an oxide of nickel together with carbon dioxide, just like you heat any other carbonate. You get an oxide together with carbon dioxide gas. Now proceeding, you're going to say that it's also a basic solid. Nickel 2 oxide is a basic solid that reacts with, being basic, it's going to react with acids. So it reacts with direct acids to form corresponding nickel 2 salts together with water. But remember that I told you it does not react with hot concentrated acids, and that is inclusive of sulfuric acid, for as long as it's hot and concentrated. Similarly, it's rendered passive by concentrated nitric acid. So nickel 2 oxide reacts with an acid, just like I said, whenever you react an acid with an oxide, we form a salt together with water. But whenever you react an element with an acid, we form a salt together with hydrogen gas. So you need to be very, very aware of that. Now let's look at the qualitative analysis that can be observed in nickel in the laboratory. So whenever you use sodium hydroxide solution on the test solution containing nickel 2 ions, one of the observations you're going to see is that you're going to see a green precipitate which is going to be insoluble in excess sodium hydroxide. It's going to be insoluble in excess sodium hydroxide. I think this was a typing error. Insoluble in excess sodium hydroxide, you exclude this. So I get, whenever I use sodium hydroxide, nickel when it's present in test solutions, it's always insoluble in sodium hydroxide. So we form nickel 2 hydroxide, which is a green precipitate, and we have said that most of the salts of nickel are going to be generally green in nature. So nickel ions react with hydroxide ions from sodium hydroxide to give us nickel 2 hydroxide, which is a green precipitate observed when we add sodium hydroxide dropwise in excess in a solution containing cobalt 2 ions. Now let's look at the ammonia solution as a reagent. So in ammonia, the hydroxide of nickel is soluble to give us a blue solution, and this is a very distinct observation about nickel, and it can be used as a confirmatory reagent. So we're going to say that green precipitate soluble in excess forming a blue solution. So the green precipitate is as a result of formation of nickel 2 hydroxide, just like explained above. Now it being soluble to give us a blue solution is due to formation of a complex of amine. So nickel 2 hydroxide reacts with 6 ammonia molecules in water to give us a complex of hexaamine nickel 2 ion, leaving hydroxide ions in solution. Now the other finalizing reagents, one of them is going to be potassium hexacyanopherrate 2 solution. Now remember that also this is the same reagent that confirms presence of iron 3 ions as a remembrance for the previous video. So the observation here is going to be a green precipitate which is going to be soluble in ammonia solution. Remember that any solute of ammonia, any salt of nickel is going to be soluble in ammonia solution. That's what you should put at the back of your mind. So nickel 2 ions reacts with a cyanoferrate 2 ions from potassium hexacyanopherrate to give us a complex which is going to be a green precipitate. But when you subject this precipitate to excess ammonia solution, ligand exchange is going to take place, and you're going to form a complex of ammonia, which is hexaamine nickel 2 ion, which exists as a blue solution. But here we just need the observation of green precipitate which is going to be soluble in ammonia full stop. You do not give further observations. Now let's go to the confirmatory reagent of nickel. So the confirmatory reagent of nickel is dimethylglyoxime solution in presence of ammonia solution, and here we form a red precipitate. Some people say red coloration, but that's incorrect. It's a red precipitate. So you tell your teachers to carry it out with you in your laboratories. And this is the confirmatory reagent of nickel. Now you do more research, or you revise these reagents more details under your practical books. Now with this, we come to the end of the chemistry of both cobalt together with nickel. I say that you advise subscribe the channel, share the video and like the video, share it to your friends so that we can all benefit together and we pass as a group. For any concerns, leave your concerns or issues in the comment section. So see you in the next video.